This film is one of the success sagas of National Institute of Ocean Technology (NIOT), a premier institution in the field of ocean technology, functioning as the technical arm of the Ministry of Earth Sciences, Government of India. The Institute's relentless efforts transformed the lives of the fisherfolk and the coastal community in the 3 fishing villages of Kadalur, located to the south of Kalpakkam in Tamil Nadu. Though the fishing boats parked on the beaches and the fisherfolk carrying out their daily activities on the wide beach of Chinnakuppam is a routine today, the shoreline had a dangerous past before 2015, as there was no beach along the shoreline. When the Fisheries Department of the Government of Tamil Nadu built several facilities at Kadalur Periyakuppam in the year 2011, the structures were originally located 60 meters away from the high tide line. The beach was stable from 1990 to 2000. But from 2010 onwards, substantial beach has been lost due to erosion, thereby leading to the scar beneath the structures. Along the east coast of India, the net movement of sediment due to wave-generated currents is towards north. These erosion-related issues are likely to happen when an engineering structure protrudes into the sea and blocks the northerly sediment movement. It was a surprise when such phenomenon occurred in the Kadalur villages, where there was no engineering structure obstructing sediment movement. In order to find a solution and restore the lost beach, the Department of Fisheries, Government of Tamil Nadu entrusted the humongous task with the Coastal and Environmental Engineering Group of NIOT. Kadalur villages consist of 3 fishing villages, namely Chinnakuppam, Periyakuppam and Adikuppam. The villages are sandwiched between 2 water bodies, Palar River on the north and Chinnapalar Creek to the south. During July 2012, large-scale erosion and substantial loss of beach was observed. NIOT scientists analyzed the site condition and started beach profiling measurements to check the monthly change in beach widths. Real-time kinematic survey equipment were used to monitor the sand volume change, which was carried out on monthly basis to understand the effect of seasons. Bathymetry of the study area, covering about 15 km stretch of shoreline, sediment sampling, wave, tide and current measurements were also carried out. Analysis of satellite imageries revealed shift in shoreline by loss of sediment over time. It was observed that the beach loss was aggravated after the occurrence of every cyclone which affected the coastal Tamil Nadu. Major damage may be attributed to cyclones: Thane in December 2011, Neelam during October 2012, Madi in December 2013 and Varda in December 2016. Based on beach profiling studies, it was estimated that maximum beach was lost during the cyclones Neelam and Madi. During other seasons, the volumes of sand deposited are not large enough to replenish the lost beach. Along the east coast of India, storms are routine phenomena during the northeast monsoon, but presently it is being observed that the intensity of storms have become severe, generating high energy waves reaching the coastline and resulting in severe beach loss. This phenomenon indicates the impact of climate change on the otherwise stable shoreline. The challenge was to design a shoreline management option that was holistic in its working. It had to mitigate erosion, result in beach restoration, whilst also not transferring the problem to the adjacent shoreline. Options for shore protection measures like groins, seawalls, shore parallel submerged dike, etc. were evaluated. A submerged shore parallel segment offshore dike was finalized to mitigate storm wave forces, in particular by making the large waves to break away from the shoreline, thereby preventing loss of beach and consequent scur. Numerical modeling using Delft 3D was carried out for various combinations of segmented submerged dike for determination of the best combination of dike segments and gaps. The final configuration consisted of a submerged dike segments each 200 meters long with gaps of 60 meter in between them. Height of dike was 3.5 meter in 4 meter water depths. A total of 7 segments covering a length of 1.76 kilometer, including gaps covering all the fishing villages, were designed. The geosynthetic material specifications were determined using relevant standards. Geosynthetic tubes of 15 meter circumference and 25 meter length have been used, this being a first project of its kind without any precedence. The Institute has carried out in-house design of various dike components, material specifications, deployment methodology for laying of submerged dike in the wave-breaking area in open coastal waters. The design has been vetted by Deltares. The dike laying methodology was based on the group's experience in laying an underwater dike in the Hooghly estuary. However, the challenge was to carry out the execution in the wave-breaking area in an open coast in 4 meter water depths, where wave forces, currents and littoral transport are severe. The methodology was designed to the minutest detail for easy implementation. The geosynthetic tubes were opened and spread on the shore and folded in a specific manner that could be easily opened before being carried to the waterfront using a crane, as each tube weighs half a ton in air. It is then loaded in small boats and taken to a jack-up barge, stationed near the proposed dike location, where it is then stored. Anchor blocks are tied to the 4 corners of the first geosynthetic tube for position fixing. The precision is achieved by moving the anchoring block using RTK GPS positioning system. The geosynthetic tube is dropped on the water by the crane and is dragged using small boat-to-dike location and is pinned to anchor blocks by divers. Sand required for filling the geosynthetic tubes is made into slurry and pumped using floating pipelines. The second tube is filled in the same manner after being fixed in position adjacent to the first tube based on GPS. The third tube is positioned on the top of first 2 tubes and filled to required height. total height of the dike unit, comprising of 3 tubes, is 3.5 meters. 8 such units form one dike segment of 200 meters. On completion of construction of dike segments, beach has started growing gradually. The beach slope is gentle, indicating accumulation of sand behind the dike area. The northernmost area beyond the last dike shows beach formation and is devoid of erosion. This methodology indicates the passive method of beach restoration, without erosion of shoreline beyond the region of shore protection, unlike groins or seawalls. The dike segment has withstood high wave generated during Varda cyclone of December 2016, thereby proving the stability of submerged dike unit. The impact of Okhi cyclone in 2017 on the Kadalur shoreline was negligible, while the shoreline of Bommayarpalayam, located 60 kilometers south of Kadalur Periyakuppam, was severely damaged. The submerged dike laying has helped in restoring the lost beach front of the fishing village and stabilized the shorefront. Presently, fishermen have started parking their boats safely on the beach after a long time and continue their routine activities on the newly formed beach. Underwater videos indicate stable dike with significant marine growth, like mollusks, which facilitate fishery development by attracting variety of fishes, crabs and lobsters. This also proves the environmental friendliness of the submerged dike solution. Successful implementation and demonstration of environmentally friendly shore protection measure based on indigenous designs by the National Institute of Ocean Technology at Kadalur villages is an initiative towards Sustainable Development Goals of United Nations Development Programme UNDP. In view of the successful outcome of this demonstration project, the government of Tamil Nadu has commended the project and announced in the budget session of 2017-18 that this strategy will be adopted for coastal protection works in all critical locations affected by sea erosion.